The blue tells us that when it turns the precision of some aquatic beam. Unfortunately, the modern era is rough. You're blind.
Very self-conscious.
Plain public bathroom that you can go to. Great. It's all the willpower. Yeah, the good thing about that side is you kind of do it from travel. We'll always have jokes. So I'm not going to.
I just think
I quietly hear this UCS scheme. I think getting another position. They also have one with Brown and Harris. I think definitely either on my job.
Yeah.
Are you doing? Pretty good. Yeah, I have a couple more classes. I definitely finished my class 12 months with my third year. What was your salaries? Your salaries?
Hello, everyone. Have you had any problem retrieving the lecture notes online for those of you who have registered? It's a little bit hidden. It's in the resources section. So you have to navigate and click twice on resources, and you'll end up finding the resources. So this week I've put the lecture notes that will be shown on screen, and I've also put a few papers that are directly connected to the things I show. Okay, so today we'll talk about singular phenomena, and there are plenty of these, and one you probably know is crumpled paper. So that's a thin sheet of paper. And naturally, and actually because of the geometry, the stress tends to focus on some very localized area. So today I'm going to introduce some mathematical tools that allow to analyze this kind of phenomena. I work in a much simpler setting than this because the plate equations are a little bit complicated to address, and there will be a lot of dimensional analysis underlying our work today. So I don't know if you guys know this proof of Pythagoras theorem. I like it a lot because it really shows the power of dimensional analysis. So I found it in Baron-Blatt's book. The argument is not by Baron-Blatt, but it's mentioned there. So consider right triangles, and of course you know that if you know the hypotenuse and one of the angles phi, then you should be able to reconstruct the triangle. So in particular, the area A should be a function of this C and phi. And by dimensional analysis, just because the area is measured in squared meters, for instance, the area must be written as C squared times a function of phi. Okay, I can prove that, it's quite easy, but this is the only way that you can make the area scale like meter square or change as you want when you change it. Then if you split the triangle into two subtriangles and notice that you have the same angles here, you can write the sum of areas as this thing, given that this would be the area of that new triangle here that has A as a hypotenuse. Okay, it's pretty obvious. And then you just have to factor out A, and you have you have Pythagoras theorem, right? So the key argument here are the triangles are similar. And I have a question for you. So what gets wrong here? What is wrong here if I move now to spherical geometry and the triangles are written on the sphere? So what part of the argument fails? What do I need to change? Because you know that Pythagoras theorem does not hold for spherical geometry. So what would be wrong?
Guess would be as a function of more than just one angle, and then
Exactly. What? Yeah. So what? It's a function also of the radius of the sphere, right? And if you have a tiny triangle much more than the radius, then it's approximately planar, and we covered that. But if the triangle has dimensions similar, comparable to the radius, then you have an extra parameter here, and then A carries an extra dependence on R, and then you can't factor out because it's not the same A's that enter into this formula. Okay, so it really shows the typical arguments that we use for dimensional analysis. So yeah, maybe you can try to explain that to a kid when they see Pythagoras theorem. It might not be a good idea because it's actually a little bit of an involved argument, but it gets simple when you start thinking this way. Okay, so now the main topic of today will be about perturbations, and actually we'll tackle the nonlinear equations of elasticity we've written down last week, but we'll find one way or another to introduce a small parameter epsilon, which can represent different things, and we'll use this parameter epsilon to solve this original problem in perturbations. And as you'll see, doing so, we can solve problems that are considerably more difficult than we could solve if there were no epsilon. So using perturbation methods simplifies our life a lot. And actually, in fact, two cases can happen when you introduce this epsilon and try to solve this problem in perturbation. So writing things very formally, so now I'm trying to find the solution X of my problem as a function of this parameter epsilon. The natural thing you would try would be to extend X as a Taylor series in epsilon and then try to solve order by order. So we see problems where the problem itself is a function of epsilon, so that could be the magnitude of the force, for instance, and then I would put epsilon in front of the external force term. And if you do that, it's along the lines of what we did at the end of last lecture. You'll try to solve things order by order. And first order, typically you have to solve some problem that involves some stiffness, the unknown, and some known right-hand side. And that's, yeah, typically what you have in linear elasticity. So when this works, this is called a regular perturbation, but there are many other examples, and we will focus on that today, where that doesn't work, and then it's called the singular perturbation problem, and you have to be a little bit more clever. So typically, that fails when anything in that problem goes wrong. So it could be that the initial stiffness is not definite. So you have some soft modes. That happens typically if you have mechanisms, or in strings problem where you have no bending rigidity. If you apply a normal load, then there's no stiffness that can carry this normal load, and this matrix essentially has zeros in some direction, so the problem is posed. And some of you might actually know how you can then correct this problem and change the expansion in the case of strings, for instance. Again, I'll give examples later. And so that's the case. Or another possibility is that when this doesn't make sense, because that's the thing you would try to solve at dominant order. So for some problems, this doesn't make sense. And for instance, you have a whole variety of X naught that are solutions, and you don't know which one to pick. And yet another possibility, well, and sometimes it's connected, is that in the solution of your problem, the solution when you expand order by order actually retains an essential dependence on the parameter epsilon. I show examples of that. So typically, that's when you have spatial features on the solution that go to a point or shrink or start to make layers as your epsilon is to zero. And again, we see many examples like that. And you recognize that this expansion is different from the first one I was giving because of this forward here, and also because of this extra dependence on epsilon. Okay, so let's do a warm-up. Oh, sorry, that's the, I'm giving a heads up on the outline of the class. So we'll warm up with a simple polynomial equation, and I'll show you in that example the difference between singular and regular perturbations. And it's actually very nice because you have all the ingredients that we need for today. Then the first big part of the lecture will be about boundary layers. So these are singular problems in statics. Okay, you're trying to solve an equilibrium. And the examples I'll be showing you is the hanging air. So it's a beam, an inextensible beam subject to its own weight, and you're trying just to classify the equilibrium shapes as a function of the weight, for instance. Okay, so that would be statics, and then we do dynamics problem where the same kind of ideas can be used. And so typically I'll be studying wave problems and long-time behaviors of wave problem, and we'll see that in these long-time behaviors, we have the same type of approaches that can be adapted, except now that we have an extra parameter time. So I've just listed the keywords that we'll be using today. You might know some of them, but these are all the main notions we'll cover. And just to make sure we're on the same page, the context here is really about nonlinear elasticity. We'll have linear constitutive behavior, but finite rotation. So the nonlinearity comes from geometry. And we'll be tackling the equations of equilibrium or the wave equation for the dynamics using some kind of expansion. Okay. Okay, so the warm-up. There's a very nice book which I highly recommend. It's really the type of book that you read and change your the way you look at things in physics or mechanics at least, because it's very elegant natural methods, and when you are aware of these methods, you start to identify many problems in mechanics that where you can naturally use these methods. So if you enjoy what I'm going to talk about today, this is really a must read. So let's start with the polynomial equation. So we're trying to solve this with respect to x, and epsilon would be our parameter. So you know it's hard to solve if epsilon is fixed because it's third order polynomial equations. But this is relatively easy to solve if you use a perturbation methods and are trying to seek an expansion of x as a power of epsilon. So how does that work? You probably would all do this way. So we grow this a little bit. Okay, so I'm just writing this equation. Now I take x as a function of e, right? So that means substitute. So this is this equation with x now function of e, and I just expand in series, right? So I use the Taylor series for x, and then I group the terms by powers of epsilon, and every equation I use, I solve it with respect to the unknown in these equations, which are the derivatives of x at the origin, right? So I turn this equation into a list of equations for my derivatives, and then I can solve, right? And then I have 3 different types of solution, and each solution in each line corresponds to a Taylor expansion of x. And this way, it's just matching, matching the coefficients in an expansion. I get the expansions for 3 different roots of the equation. So the way you would do that naively would be just to take e equals 0 here, and then the equations that's quite simple. So you just take directly e equals 0. So the roots are, and then for each, so this would be an x naught, and then you would seek a full series that solves your problem. Okay? Okay, now let's change a little bit so that's the regular problem where everything works. let's change the problem a little bit and go to the singular case. And see what happens. In the circular case, I start the same way, and I start by setting epsilon equals 0, and then my equation is minus x to the cube plus 8 equals 0, and the roots are 1 omega square, where omega is the square root of 1 minus a I to pi over 3. The cube root, sorry, of 1 of unit. Sorry, and there's a 2 missing. Okay, so I have these 3 roots, and with these 3 roots, I can do the same thing here. I can plug into the equation, and I get some expansion for the 3 roots. So that would be the x naught, right? Because I've set epsilon equals 0. And so for these 3 roots, everything works. But now you see that we have when epsilon is on 0, we have a polynomial equation of order 6, and with just 3 roots. So 3 other roots have disappeared. Okay, and it's quite easy to see what's happened. When I take epsilon go to 0, I've changed the order of the polynomial. I went from 6 to 3, and doing so, I've lost something. And that's typical of a singular problem where when you take the limit by brute force, by setting epsilon equals 0, you change the nature of the problem. So what happens exactly here is actually not so difficult to guess. Can you see, how far can you see at the back? This is low, right? It's okay? Okay, so what happens here is that there are actually 3 other roots that are not bounded as epsilon go to 0. And so you might want to seek other roots that depend on p on epsilon with some power p. Okay, and if p is negative, then it could be that this is not negligible when epsilon goes to 0, so it was not correct to remove this term. Okay, so in other words, I was implicitly assuming that x was bounded when I ignored this term for epsilon goes to 0. Okay, so now you assume this form, and it's typical of the analysis of singular problem. You're going to seek the values of p that are compatible with this equation. And the problem is that I have 4 terms, and I need to identify 2 that are the dominant one in the limit. Okay, so we said that I'm looking at the balance, the possible balances in the equation. So epsilon 2x6 would then be epsilon to the power 2 plus 6p. Okay? This would be to the power 1 plus 4p, this would be 3p, and this would be 0, right? So the question is, if I want this equation to make sense in the limit, I need to identify at least 2 terms that are dominant over all the other ones and balanced together. So that can be solved graphically. So that would be the p parameter. And then I can try the power of each of these things. So that would be 2 plus 6p. I could have 4p. I have, no, sorry, that's 4p plus 1. So let's say this is 3p. So the third term. I have 4p plus 1. And I have 8. Okay? So now, so this is the total power in epsilon, and the dominant terms will be those that have the lowest power, right? Because it diverges more. And I'm looking for values of p where 2 of these terms are balanced. So that means I have an intersection like happens here. Here, here, here. Any intersection that's happening at the minimum value corresponds to that material. Is that okay? So I just have to plot these things. I did it by hand, but you can do it on the computer. And okay, that's easy. So in our case, my drawing is wrong, and with these specific values, I only have 2 intersections, so that gives me 2 values of p. And actually, if you do the math, for my problem, I have P equals -1/3 and P equals 0 are the two options. So -1/3, I forgot the details, let's see. -1/3 would be probably, see, I forgot that I needed the numerical values. Can you help me identifying the terms that are balanced? I'm pretty sure it's -1/3. So that would be 0, right. So if x is -1/3, this is of order 1. This is positive, I guess. So I think these ones are balanced, right? And dominant over the other ones. So let me take this case. Then the dominant terms in my equation is epsilon2 plus x. This is, I hope I'm assuming correctly. And so I have a solution which is x goes like -8. That would be -1. I'm not sure the calculation is correct, but I mean, I do that very formally. It's easy to correct if my numbers are wrong. Okay, so that's one solution. And so now, what about P equals 0, which is my other solution? So guess what? P equals 0 is just these two terms, and that's exactly what we did before. Right? Okay. So now, so let's focus on this case, because this one we have already solved. The question is, how can I continue the expansion for x? Well, it's pretty natural to look for x. Now, you know that it starts as epsilon -1/3. So I'm going to define a rescaled variable, it's called a stretch variable, where I already use, well, the idea is that this one stays bounded, and because we factor out the divergence that we know. So the idea is to introduce this new stretch variable and now write the problem in terms of x. So you just insert into the original equation, and what you find is that for x bar, you have a regular problem now. So just by switching to this variable, after we have identified the type of divergence, we managed to remove the singularity, if you want, and turn our singular problem into a regular problem. Okay, so let me recap just the approach, because that's exactly what we're going to use for more complicated problem. We identify a singular problem when we see that something fundamental in the problem changes in the limit, and we are losing solutions because it's too harsh an approximation to directly set epsilon equals 0 in the problem. Then we look for singular behavior, and we do that by scaling analysis by trying to balance terms. And then once we have done that, this allows us to introduce stretch variables. Okay, and again, that's the same ingredients we use later. Okay, so Warmup is over. And let's apply that to a slightly more interesting problem. So I'll consider what's arguably the simplest problem in nonlinear structure mechanics. So it's a 1D beam, a 1D elastic that's subject to its own weight and is inextensible. Okay, so I'm applying distributed weight. So rho would be the mass density per unit length, g is the gravity. And this problem can be formulated as a minimization problem where we would typically use the direction of the tangent theta as the main unknown. We are clamping here, so we impose the value of theta at the origin 0. Then in terms of theta, we reconstruct the elevation at any given point. This is z by, well, integrating along this curve and integrating the sine, so that would be at the elevation. It's a beam, so we use the curvature of theta prime well, the theta prime would be the curvature, so that's the rate of change of angle with respect to arc length. And then we prescribe some natural curvature, kappa naught. And so the curvature strength will be the change in the actual curvature minus the reference curvature. Okay? So with all these ingredients, you can seek minimizers, so or shapes that will be stationary solutions. We are not going to be worried about equilibrium, so let's just say stationary solutions, stationary points, sorry, of this integral, right? So B would be the bending modulus, that's the change of curvature square, and that's the potential energy that represents the effect of weight. Yeah?
What was kappa naught?
Sorry?
What was kappa naught?
Kappa naught would be the natural curvature. So if you remove gravity, G equals 0, you don't have this term. That would be minimum by having the curvature, means kappa naught. That would be the natural curling of the hair. Okay.
It's a constant.
I take it as a constant, but then you can make it space dependent if you like. The analysis is just simpler if it's constant. Okay, so now you can try to derive the Euler-Lagrange equations, the equilibrium equations, by using the Euler-Lagrange method. I'm going to skip this and just give you the answer. And actually, the final equations have a simple interpretation. So I won't go into the details of deriving that, but it's a small exercise. It's a nice exercise in the calculus of variations. There's one little trick that because we use this theta variable and z here, you need to swap. So there's a double integral when you insert that in that, and you need to swap the integration variables, and that makes appear this factor here, which has a very simple interpretation in terms of mechanics. So that would be the equations of equilibrium. That's the gradient of moment, right? So that's a balance of moment on the small element. So this would be the equilibrium in the interior. That's the clamping condition where theta naught would be the parameter of the problem, and that's the condition of a free end here. That, well, actually the moment is 0, and so by the quantity of the curvature, there's no B here. The curvature has to match the natural curvature. Okay, so we derive that by the calculus of variation. There's an interpretation of this equation if you know the nonlinear rod theory, but you don't even need that. So if you view this as a nonlinear rod, an elastica, you know that at any given point R, there's an internal force R of S. So it's the force that you get when you cut. And so it's the integral of the contact force on the small cut section. That's written like that, just because this is the weight of the hanging part. And this force achieves an equilibrium of this hanging part, right? And now for an elastica, the equilibrium of moments, right? Derivative of moment plus tangent cross internal force equals 0, and that's exactly this equation. Okay, so either way, just either using the general rod theory or by the Euler-Lagrange variations, you get to that equation. Okay, so before we do some analysis, let's try to turn this problem into a dimensionless form because it's so much easier to do the analysis later. So the first obvious rescaling is to use a new function theta with a bar on top that makes use of a rescaled length. So instead of S, I'm using S bar, which is S over L. And that way I avoid to introduce an explicit length in my, well, I remove the explicit length in my problem. I'm assuming that you're familiar with this step. You just have to insert this into the equation, paying attention to the fact that now the derivatives here involve an extra L factor compared to the derivative of the original function. And actually, this extra L factor is beneficial because it combines with the other terms and makes appear dimensionless parameters of the equation. And these dimensionless parameters are really those that capture, the essential features of the solution. So if you do that, so remember, this is the weight of any part of the rod which is below, and this dependence on S captures the fact that this is less subject to tension than this part. This beta is a scaled bending modulus, and it's been scaled by the weight, right? So that's really the balance of weight and gravity, which are the two main effects in our problem. And in the boundary condition here, you see the natural curvature that resurfaces. And in dimensionless form, it's the typical number of turns that the rod makes without gravity, right? So that's the curvature times the length. I'm ignoring any factor. Okay. So effectively, we've simplified the equations by effectively taking all these coefficients equal by 1, and we've removed them by this dimensional analysis. Okay, so I'm going to stick to this formulation from now on, but I'm dropping the bars just because it's more readable. So in other words, I'm using this as a convention and omitting the bar. So this is a nonlinear boundary value problem. Okay, I'm looking for these functions theta. There are some numerical methods to solve that. You can use a shooting method. You could use 1D finite elements and energy minimization. You could do all kinds of things. We focus on analytical approaches, and basically the question is, when you set alpha and beta and theta 0, okay, what can you tell about the solution theta? Can you construct explicit solutions, etc.? I'm going to just give you a sense of the solution by, so the benefit of working in 1D is that it's very easy to simulate the solutions, and you can have interactive solutions, etc. So you can just play with this and change the length. Okay, so for very short hair, you remember that this beta is the ratio of the stiffness to the total weight. So for shorter hair, the stiffness is more important because the total weight scales like the length. And that's exactly what you see here. If I make it shorter, that's essentially an arc of circle. I can change the natural curvature one way or the other, making it longer. And you see this nice balance of, well, you understand the shape, right? This is stretched by its own weight. So the weight of this part is large. It's pulling to the bottom, to the downwards. And then if you go further down, you recover the natural curvature because the weight is not that big. So in words, we understand what we have here. And so what else could I have? I could also increase again the natural curvature. And then you have this kind of fancy typical hair shapes. And that's why L'Oreal got interested in this type of model. But I really use that as an excuse for introducing this boundary layers equation. And you'll see where the boundary layers are. Okay, so that looks like a hard problem. Essentially because of the cosine and the double derivatives, I don't really know how to find explicit solutions. But we can use this idea of letting one of the parameters to 0 and look at the limit of a very heavy, very light, very curved hair and see if in these limits we can find solutions. So the first thing we do is to move the beta here, so divide by beta, and so we have 1 over beta here. So now this is the weight, right? Remember, this is the pulling force. And then we can look at beta minus 1 as a small parameter. So that means we are taking a light or short hair. And we can seek solutions of this problem in perturbations. I mean, this used to be a polynomial equation. Now that's a boundary value problem. I'm still looking for solutions in perturbation. And we are happy that in that case, this is a regular perturbation. And you can just see that by inserting this expansion. So now I'm inserting in terms of this parameter. So at order beta to the power 0, I just remove this term. Okay. And I have this, but this is obvious. This is my natural configuration. It's like switching off the weight. Okay, so that's the natural shape, and the solution of this is just an arc of circle. I can switch. I can push to the next order, and I have on the left-hand side a differential problem that for this theta 1, and on the right-hand side something which now is known from the previous order. Okay, and that's now much easier because it's a linear boundary value problem. And the linear boundary value problem is just a problem of well, you look for a homogeneous solution. You can use the method of the variation of constants. They are analytical solutions. It's not very difficult to do. And actually, there's a nice interpretation for that. This is exactly what you would do if you do mechanics of materials, where you have structures with an infinitesimal load, and you're doing linear elasticity. So you use the reference configuration. You assume that the load is applied in the reference configuration. You convert that distribution of loads into internal forces, moments, everything in the reference configuration. That's exactly what you're doing here. And this is the reference configuration that's used for the geometry, right? So this is exactly equivalent to what you know in the strength of material, or mechanics I think it's called strength of material, right? It's linear elasticity. So strength. Okay, so that was easy. Small, light structures stay close to reference configuration, and you can just treat the weight as a perturbation, and you have small corrections you can always have. So let's say something more interesting now is if we want to have a strong gravity, which is more realistic for hair, especially long hair, it's something which is going to go down and forget about its natural curvature almost everywhere. So the weight is winning in some sense. Now the interesting thing here is that this is now a singular problem, and you can realize that if you take directly beta equals 0, you kill that derivative term, and then you have something which is no longer a differential equation, but has still two boundary conditions, and the boundary conditions are incompatible in general with the term that is left over here. So your problem is broken in the limit. Okay, you can't just directly set big tau equals 0. Sergio, are you? Okay.
I'm just trying to think about the uniqueness of that solution.
Ooh.
Is it really unique? It
No.
probably is, but I don't.
No, it's not. I mean, it's a nonlinear problem. So maybe in some small parameters range, it's not. So typically, you can if you have a vertical, even if you have a clamping at an angle, you can go this way and fall, or you can go this way and fall, and both are even stable. So no, it's really not unique. Thanks. Okay, so what can you do then to address this situation? Well, if you look at the solution, you start to realize what's happening. So it's heavy, right? So it will be vertical most of the almost everywhere, except in a small region here where it has to bend to accommodate with the clamped angle. Okay, so we're really, and in some sense, discarding this term here, like you would do naively, is not too bad in this region, because then the cancellation of this term gives you vertical sections. But it's bad only in the neighborhood of where you are applying the boundary conditions. Okay, so that's really the notion of boundary layers. In small layers, so in small region close to the boundaries, typically, but boundary layers can also appear in the interior for some more complicated problem, but not for today. So in some regions, there's a different kind of behavior than in the interval. Okay, so we can implement what we did for the polynomials, and we can try to do some scaling analysis to get a sense of what is the size of this layer, for instance. So how large is this region? And it's actually pretty, well, for that example, it's not too difficult. It will be more difficult later. So let's say in this region, by definition, that's where the two terms are of similar magnitudes. Beta is small, but the curvature and the derivatives of theta are large, and that ultimately balances this term here and here. So let's just try to balance the two terms. The first term, beta. Oh, first I need to find estimates for the various quantities. So what would be the order of magnitude of theta? Well, theta varies from 3 pi over 2 here to some finite value that's set by the boundary condition. So the range of theta is 1, right? It changes by values of order 1. So that would be theta. So now let me call delta the size of the boundary layer. Okay, so any s I have in the equation would be of order delta in the boundary layer. And again, I'm doing scaling analysis. So I'm just trying to find all those values, and I'm discarding any coefficient that would be. Okay, so now we can balance this first term. So that would beta, the small number, times theta, which is of order 1. And there's two derivatives, so that's delta squared. And the second term would be, so that's the weight, right? So this is the weight of the entire structure and our dimensionless variables, and that's the weight of any part that's below a given point, but S is small. So I'm going to assume that delta is small, and I'll check that it's consistent later. So I can just approximate 1 minus S by 1, and I'm left with cosine theta. And cosine theta is just of order 1, right? So I did the scaling analysis similar to finding the exponents P we had for the polynomial equation, and now I find that delta has to be of order beta, square root, right? And that's consistent because we assume that we are taking the limit where beta is small, and that's small. It's of a different order of magnitude, but it's still small in front of 1. So it was consistent to neglect the term 1 minus S. Okay, so it's always a lot of fun to do this scaling analysis. It's never difficult. You just have to play with the terms and be a little bit creative. Sometimes you have to try different things, and you should always end up with something that works. Okay, so now if we have this, it makes sense to try a rescaling. So now remember, I dropped the bars for the first dimension time I went dimensionless. So now I'm using a different bar. I forgot about the first one. So this is yet another rescale function. So I'm going to define theta S. Well, actually, it's written here. So S is for scalp, because we're close to the scalp. Okay. This lowercase s is my rescaled arc length. Okay, so the lowercase s is the original s divided by delta. So this s now is another stretch variable. Okay, it's the natural variable that you want to use if you're looking at this region. And actually, by design, it's done in such a way that lowercase s is of order 1 when you're somewhere in the middle of the boundary layer. Okay, and now remember, I use the fact that theta is of order 1, so I don't rescale theta, but if that were not the case, I could have added some power of beta in front of theta, right? So the point of this rescaled function theta is that it depends on the dimensionless variable that's of order 1 in the boundary layer, and its value is of order 1 in the boundary layer. So it's a pure function, everything is of order 1. Okay, and I can just take this and insert into that, and this is what you get. Okay, so I'll actually do two things. You insert this into this, and you retain all the dominant order terms in beta. Okay, so there are small corrections that I've removed. And remember, this is exactly the same type of method that we use for the polynomial equation, and I said that the rescale problem had become regular. And well, this is regular. This looks like a perfectly nice boundary value problem, except for one thing here. Okay, so for these two parts, it's simple. Actually, yeah, I mean, it's pretty easy. So the one is here, and the S here has become now this quantity. It has no value. Okay, and I'm just discarding this one in this equation. So that's the dominant order equation that I get in the boundary layer. Okay, so that comes obviously from the clamping condition. And now the question is, what do I do with that?
Question. So with the boundary condition as S goes to infinity, is that something that you come up with just by kind of looking at the problem and saying, oh, this is what we expect the solution to kind of behave like? So we're going to...
Sorry, I missed the beginning of the question.
The theta S bar as S goes to infinity is 3 pi over 2.
Right, I'm coming to that.
Okay.
I'm coming to that.
Well, is that just something that you get by looking at the problem and assuming this is the solution, or is it something that...
So that's the trick. That's the trickiest part. So the thing is that the first thing, you should not try to use this equation, and we'll come back to that later, because when the origin variable is 1, the rescale variable is very large, and actually the region where it is applied is beyond the region where these approximations are valid. Okay? So these two are easy, and usually what you do here is that now you look at the equation and what are the possible behaviors of this equation for large S. Okay, so large S meaning I'm exiting from the boundary layer. And now, and actually it's something you can actually do later, so you can leave that undetermined for the moment. But typically what you do here is that you will select among all the possible asymptotic behaviors of this equation for large S. You will impose those that are consistent with what you expect outside. So it's called the matching problem. I'm going to come back later to that. And so this equation reinforces that you'll be consistent with what you have here in this outer region. Okay, so I'll be a little bit fuzzy on that for the moment. Okay, so that's nice because the parameter beta has been removed. It's a parameterless problem, and you can typically use, well, you have to be a bit careful whether this and this warrants unicity of the solutions. For this problem, it's the case. I'm not going to give too many details on that. And it even happens that this problem has a unique solution that can be written explicitly, and the solution is doing exactly what you expect. So just by hand, if you try to plot the profile here of theta, it's varying from the initial value to 3 pi over 2 here. And then it has this asymptote here, which corresponds to that. And then this function does exactly that, right? So there's an extra parameter S naught here, which actually you can tune to achieve this equation. So S naught would be a function of theta naught. And to return to your question, Sergio have required that it goes to 3 pi over 2 here because I was expecting that it was doing a single turn. But you can add 2 pi here, and that would be something that does several turns, and then you consider that this solution. So yeah, you can do as many turns as you want, essentially. At least in the limit of high gravity. Okay. So that's the boundary layer. Okay, we have an explicit solution. We've managed to remove the S by using Prandtl variables and rescaling the equation. Okay. Now, what happens near the free end? You might have seen in the simulations that the tip lifts off a little bit from the vertical, and that's because of the applied curvature. Well, essentially the same thing is happening. So we're still looking at the limit beta goes to 0, but now at the other boundary. And there's again this problem that if we kill beta directly here, we have theta equals 3 pi over 2, and that's inconsistent with this condition if alpha is non-zero. So we can try to do the same thing and derive some boundary layer solution here. It's a little bit more interesting. So what are the terms we need to balance? Well, obviously these two terms, because there are only two terms in the equation. This we won't use because it was relevant to the other boundary, and we are speaking of a different boundary now. And these two terms need to be balanced too, because alpha, it's obviously what is creating this behavior from the beginning, right? So let's use this one first. So let's say that theta, the variations of theta, so that's the deflection angle if you want. Let me call it capital theta. So any derivative of theta will scale like capital theta, right? That's the typical variation. So the equation theta equals to alpha, if you look at it in orders of magnitude, that says that the order of magnitude of the variations of theta divided by the scale here, which I call delta, but which would actually be different, so there's a small conflict of notation. This is a new delta. Okay, so that's what the boundary layer is telling me. And now let's look at the equation here. So we have beta theta second derivative that I have to balance with the other term. So what is 1 minus s now? 0. It's never good to say that. I mean, when you do orders of magnitude, it's never good to have 0 because. So you have to think you're in this boundary layer somewhere, typically here, and you have to assume that the order of magnitude argument will be the same everywhere in the boundary layer. So the typical value of this would be delta, right? Delta by the drawing is exactly how far I'm from the boundary. So that would be delta. And what's the value of the cosine? It's a tricky question. Well, let's look at it the good way. It's a question that has several different right answers. Correct answers. Okay, so if you look at here, cosine theta is 0. Okay, so let's assume that this theta is small, and that's something we can check afterwards. Well, then if the deflection angle is small, then you can linearize the cosine, and the cosine is of the theta. Okay, so that would be a curl that deflects slightly from the vertical. We'll see later another possibility where everything is localized, but it starts to make curls here. So theta is no longer small, but that's for later. Okay, let's assume that theta is small for the moment, and we'll see that it yields a condition on the parameter. Okay, well, theta can be eliminated here, and you find that delta is now beta to the power 1/3, so the cube root is larger. The extent of this boundary layer is larger, and you can find theta, which is alpha beta 1/3 from this equation. Okay, so that's the scaling of the size of the boundary layer, which we use to rescale everything. And this is used to check, this can be used to check our assumption, right? So this is going to be correct as long as in absolute value. Okay, so remember beta is small. So that can even work if alpha is large for very curly hair, as long as this combination of the two is small. If that starts to be wrong, I mean, if this is not satisfied, we'll talk about this later. Okay, then you can redo the same trick as earlier. We scale the theta now f, like 3n, by what we've just found here, which is the scale of theta. So you rescale theta minus 3 pi over 2, which is our deflection. You rescale it by the typical deflection we found, and you express it in terms of this dimension, new dimension as variable t. But now t is defined with the new scale beta to the 1 minus 2. Okay? And the beauty of this, again, this is relatively simple. You just have to identify the terms in the equation that play a role, balance them. And the beauty of this is that now, if you insert this into the equation by design, this is done such that all those small parameters beta are removed, they disappear, right? And you end up with that equation that has no parameter. Okay, so again, this equation is just this one. The t here comes from the 1 minus s, and the cosine theta has been linearized. The beta has been absorbed by the rescaling. That's this condition, so there's a -1 because there's a minus here. And that again is a matching condition. We'll come back to it later. That because we have exponentially diverging solutions for that, which we are not interested in. We are interested in those conditions that connect with this. And that's theta bar equals 0, or the original theta equals 3 pi over 2. Okay, again, you will need some work to prove where there's uniqueness, etc. Here, I'm almost sure there is, but I couldn't prove it right now. And the nice thing about it is that this is okay. So it's a boundary problem that stretches to infinity, and there's actually a unique solution, and this solution is actually well known. It's called the Airy function. Okay, not to be confused with the Airy potential inelasticity. It's just a pure mathematical function. Okay. So it's a function that, again, gives exactly this type of profile. It's known. It can be. You could also calculate it numerically if you prefer. And we have solved everything in that region. Okay? So now, where are we? We have two different types of approximations in two different regions. We have the scalp here, has a thickness beta to the square root of beta, and we have the free end that has a thickness cube root of beta. We have two different rescalings. We have explicit solutions. So these now are two known functions. And so what can we do with this? Well, by design, we have made sure that these two functions in this region in the middle go to 3 pi over 2, right? So by design, we've made sure that they are consistent. So we can just define some kind of composite approximation where we have a global function that can be evaluated by whatever formula you want in the matching region, because they are by design consistent. And then if you are here, you need to use the relevant approximation. Okay. So the key thing here, when we move from local approximation to proposing a global solution, is to make sure that there's a region of overlap where the two solutions agree. Okay? And the good news is that there's a very deep reason why the two solutions agree. And you can understand that by looking back at our equations. So that was the original equation, remember? When we did the scalp approximation, so the approximation at the top, the idea was to approximate this by 1. Remember, because S was small. And that's the weight of whatever is pulling. We can just approximate it by the entire weight. Okay, so that's the equation we arrived. Now, when you exit from the boundary layer here, you take large S here. And essentially, you can convince yourself that you're killing this term. So the large S asymptotics of the boundary layer equation is just this term. Okay? So what did we do now when we came from the other side? From the other side, we retain this term here, but we linearized the cosine. That was our main approximation. Okay, so we linearize the cosine, and now what happens if you move back to the matching region? It's again the same type of argument that this is damped out, and you have to you have to connect with the roots of this thing. Okay, and that's really why the matching works. Is that whatever approximation you do in one boundary layer, whatever approximation you do in another boundary layer, when you take the limits and see what's happening inside, you're going to the least common denominator of all the approximations you've done. Okay. So I can't explain to you in very general terms, and some matching problems are more difficult than others. We'll see some later. But there's this argument everywhere that this is a particularly easy region where any kind of approximation would work, and that's why you can match whatever comes from one boundary layer or the other. Okay, so boundary layers problem are like that. You analyze what happens in the boundary. You use stretch variables. You solve the problem in stretch variables where you've removed singularity. Then you analyze the large S or large arc length asymptotics of your singularity, and then you try to match with what comes from what is called the outer solution. The outer solution is the solution which has no problem, which is smooth. Okay. Okay. Now remember, the validity is that we have assumed that the weight was large, and now we found this extra condition of what happens when there's a small deflection. We have assumed that the deflection was small, and just to make our life easier, and so we have this extra condition. So alpha can be large, but not too large. Okay, so maybe it's a little bit of a side question. You can ask what happens now if this parameter, if alpha beta, if this parameter is now large. So that's when you start to have loops. And okay, I'm probably not going to give any details on that, but you can construct a solution that's a periodic solution, but slowly varying, right? And what happens here is that locally, you have curls like that that are determined by the amount of stretching force that you have. And because beta is small, the stretching force changes on a scale that's much larger than the period of the curls, right? So you can use, I mean, it's a good approximation locally to assume that the curls are periodic, but if you move globally, the period changes, and it's similar to a classical problem in rational mechanics, where you have an oscillator that's some particle that's oscillating in the potential, and you're slowly changing the properties of the potential by changing the force or something. So it's called the adiabatic oscillator, and you're interested in knowing what would be the trajectories when you're changing these properties continuously. So this is a different question. I'm not going to give more details on that. And so very quickly, a tentative phase diagram for our simple problem. We have the light case here, heavy case here, highly curled, almost straight. So some of the drawings are pretty obvious, like this one, with this boundary here, where we go from a small deflection at the end to several curls, and then there's another boundary which I'm not discussing, where all these curls, everything winds up and you touch the scalp, right? So that's what you can do. And in every of these regions, you can devise specific approximations and find solution. Okay, now you can ask what the problem would be in 3D. 3D is actually a little bit simpler, because these curls that you have, they become helices, and helices you can change continuously from a straight thing to a helix, right? So in some sense, 3D is simpler, because here typically you have helices of small amplitude, which is easier to describe than these finite amplitude curls. But you get the same types of patterns. You see you have the planar shapes that we had before, and that's and then you have at some point some instability where you go 3D, but it's the same thing, that the load or the tension is lower at the bottom, and you see more something that looks like the natural curvature as you go to the bottom. And I think I've included our paper that analyzes this problem on the online repository. Okay, and now I really want to give you a few examples where exactly the same type of ideas can be applied to completely different systems. So this is a knot tied in a stiff nitinol rod. So that's an example where we did a double knot. It's not a trefoil knot. We went twice around the thing. And that can be studied by exactly the same type of method. So it's not really obvious here, especially with double knot, but you can, it's probably clear for this one, which is a simple one. So that's a big loop, which I haven't represented. And the question is, what is the equilibrium evolution for the bond? So it looks like a terrible problem that has self-contact, finite rotations, etc., etc. But if you realize that this is a small region compared to the loop, you can do a boundary layer analysis here. And then you can analyze the self-contact in this region where the angles are actually small, like we did when we linearized the cosine theta. So it's self-contact, but it's linear. And it's actually, just by the principle of linear superposition, this problem is equivalent to a rod winding around a hard cylinder. Okay? Just take the difference between the two rods, and that's effectively a rod winding around a fixed obstacle. So it's a fixed contact problem, and it's easier. Okay, and you can study everything like that. And one of the funny outcomes we didn't even expect, that we looked at the picture, and there's a small light that comes through here. And actually, in the elastic solution, the contact is a point light contact here, extended contact in the middle, and point light contact here. So you can do all the geometry and use the asymptotically exact solution that we derived and find the length of this light that you see. And it's just you have an explicit formula in terms of the geometric parameters of the rod, and it works really nicely. It's exactly what you see in the picture. So it's a small detail, but it's an independent validation of it. There are many other situations where you can use the same type of theory. So one example, and again, there are so many others, is this. That's a paper that was published last year. So they have this column elastic column with big holes that are almost tangent to the outer boundary, and when they deform it, the deformation gets focused in these tiny bridges, right? And they do exactly the same kind of analysis here. So they would typically use an elastica solution here. That's an elastica with variable cross-section, but it's still an elastica, so you can characterize the bending rigidity typically. And then you would match to this region, which is a rigid body. And so you have, I mean, if you assume that the thickness of this ridge is a small parameter, it's exactly the same method, right? You have a global elasticity solution which is hard to characterize, but then you can show that the deformation is localized. You can come up with specific approximations here, and you can show that this is recurrency equivalent to rigid bodies connected by hinges. I mean, and it's purely it's exact in some sense, right? There's no approximation in doing that. It's going to be asymptotically correct when this length is much smaller than the width of the body, right? And then you can use that to so you have then you have a series of hinges and rigid bodies, and you can use to study the instabilities of this column, for example. Another problem is when you crush a ping pong ball, or when you do experiments on spherical shells with internal pressure, you have these solutions where the cap has been inverted, and that's the reason why this is a beneficial deformation, is that preserves length, right? So it's good for the membrane part of the stretching energy. There's no stretching energy involved in this inversion, but then there's a problem here because you have infinite curvature. Okay, so that would be this picture here is what we call the outer solution. It's like the vertical part of the ridge, and then there's a problem at some point where you have to devise different types of approximation, and so that can be done by introducing scales, analyzing the optimal curvature here that tries to please both the stretching energy and the bending energy, and you can come up with a specific theory here. And then you can match everything, and then you can interpret you can calculate the elastic and the effective energy of these ridges in a way that does the microscopic solution of the problem. Okay, so I'm just trying to make the point that when you start when you know these methods, there are many examples, especially with thin structures, where they can be used. And again, that's a way to tackle the nonlinear problems which otherwise are hopeless to solve if you don't have a small parameter. Okay, so I was going to go to the second part of my talk. Do you need a few minutes of pause, or do I just go ahead? Okay. So it's going to be quick, but I would like to give you a few hints on how these solutions can be used for wave problems also. So there's a very nice book by Prandtl, which I referred to in the beginning when I was speaking of this demonstration of Pythagoras' theorem, which is concerned with self-similarity and asymptotic. So the argument, I think it's pretty clear from a simple picture here. So assume you have some continuum that transmits waves, and you have an initial disturbance that takes place on some wavelength h. Okay, and that's perturbed, and then you have waves that are emitted from there. So that at early times, so meaning for times that are of the order h over c, where c is the propagation velocity, then the problem is complicated because you have the boundary, you have waves going into directions, and it's a little bit complicated. There's no simple solution. However, if you wait until the propagation length ct is much larger than h, essentially these waves have reflected, and you just see one traveling wave that moves to the right. Okay? And then in that, for these times, the solution is quite simple. It's a propagating wave to the right. Okay? And then that's going to hold true unless you mess up with the other boundary, and that's when the time is off over L over C. And so Prandtl makes these very nice arguments that, okay, this is for a very, very specific simple wave equation, but the argument is exactly the same for any type of wave equation. It can be nonlinear, it can be dispersive, whatever. If you wait times where the microscopic features of whatever you created in the first place have, well, if you wait long enough so that these microscopic features, well, you're talking on a scale which is much larger than these microscopic features, and you're smaller than the scale of the system, then in any circumstance, and that can be shown by scaling analysis, you expect that your solution is not going to depend separately on position and space, but depend on them in a combined manner. And that's a very good news, because it means that the long time behavior of your system can effectively be reduced to seeking the solution of a single effective variable that captures times and position. Okay. So it's pretty obvious for the simple wave equation, because you all know that. But let me show you another example where this is quite powerful. Okay, so we were essentially asking the same question, and so that's the spaghetti problem. The question we were asking is, if you take a dry piece of spaghetti, and that's an old work with Sebastian Kirsch, if you take a dry piece of spaghetti and hold it firmly with your two hands, at some point it will break, and what you see is that it doesn't just break into pieces, but it breaks in many fragments, typically 5, 3, depends how dry the weather is, and but it's very often more than 2. And the question is, how comes, right? So one idea was that if you start from a bent piece of spaghetti, so that would be just 1/2 of the entire pasta, and if you release it suddenly from one end, keeping the other end clamped, so this release here would be mimicking the first breaking event. Now we are looking at 1/2 of the pasta, and the idea here is that the flexural waves dynamics that follow this event increases the curvature transiently. And that's actually what you see on the picture. If you do the oscillating circle here, it's more curved than the original. So that's just a release again. And so yeah, there's an increasing curvature that travels along the rod, and at some point, and here also it gets enhanced by reflection, but that's another issue. At some point, it manages to break the rod at some other point. So it's really a cascade where a first breaking event in a uniform landscape of curvature is going to send a wave that's going to transiently enhance the curvature, and so induce a second breaking event. Okay, so it's essentially, the way we studied that was essentially to use a Prandtl method where we look at, so h now would be the thickness of the rod. If the time is of order h/c, you would need a 3D model for the rod. Okay, there's fracture, it's a 3D problem. But now we're interested in times that are much larger than h/L, and at least here, smaller than the travel time for the entire rod. And actually, I shouldn't say h/c because there's no velocity. So it's a little bit of a crude approximation, but we use linear waves here. Normally, it's only for small deflection, but we can still try. And so we have this ODE, which is a dispersive wave equation for the curvature. We start with an initial curvature, which is constant, and we use a clamping condition on one end. And we are looking for kind of propagating waves here. But you know that propagating waves don't work, right? I can try. You know that this doesn't work because these are dispersive equation, and you can't, there's no velocity c associated with this equation, and that doesn't work. However, what you find from this equation is that there's a natural scaling where S is essentially the square root of t. So that suggests doing something that replaces these propagating waves, and this is looking for a solution in this form. You're going to look for a solution in this form. So U, so that's that would be my. And now U is a function of C, and C is inspired by this scaling because S goes like the square root of T, so we could look for U now function of S over T, right? And it's a little bit like in the previous slide. So I've shown you that in the long term, there's this combined variable that combines X and T. So it combines it this way for a simple wave equation, but it will be combined this way for this other equation. Okay? And you can just try insert this special form into the original equation, into the boundary condition, and you have a set of equations which are well posed, and the solution looks like that. And that's the good news. Okay, so just by inserting this special form into the equation, that's what you get. So now you can reconstruct the entire solution at different times. So now that would be the curvature as a function of position for different times. So at early times, this one is small and this one gets shrinked. So that at very early times, there would be something like that. And then as time passes, this gets stretched out. So it's that would be later time, and that would be later. Okay. At very, very early time, this solution is not rigorously valid because I said that this uses beam equations, and you need to wait a little bit before any details associated with the cross-section bear out. But what you get here is actually a very good approximation of what you get if you simulate this equation using the direct method. So, and that captures, so now you see why this is compatible with the idea of cascading cracks. It's just that this solution has an overshoot, so it's 40% higher than the asymptotic value. So the asymptotic value has to match with the imposed curvature, and that solution predicts that transiently the curvature is going to be increased by 40% as this wave passes. Okay. So I think this is nice. This connects also with the first part of the talk, because now we are starting to introduce rescaling of the variables in a way that depends with time. Okay, so it's the same kind of ideas, and so for the boundary layer problems, the benefit was that we had the dimensionless problem, which is solvable in the boundary layers. And now we have a problem. We have a problem that only has one variable, and which captures the long time dynamics. Okay. So now, since I just have 10 minutes, I'm not sure. Should I give you a quick? Yeah, maybe just a sense of one other problem I wanted to talk about. It's going to be a very shallow, high-level description, but that's fine. At least you see the movies. So another problem that's of the similar type is, so we were asking with Pierre-Thomas Brun, which is a former PhD student, what happens if you take a circular spring that has many coils, you lay it flat on the table, and you release it from one end. Okay. So these are fast camera images. Up, and you see so it's rolling up, and it's a dynamic problem. So inertia enters into play. It's making this nice spiral. And then at some point, look at all the details of the solution is going to be. You see, you have a nice curl that comes in. You have many turns that are almost on top of each other, and then at some point it crashes on a book. So the question we have been asking is, can we describe, so there's some biological motivation in a different regime where viscosity is a dominant force. So the simple question with that is, what selects the velocity of this thing? It looks like a front, right? It looks like a propagating waves, but how can we guess the velocity of this? So you can first do a simple scaling analysis. So you can model this as a linear elastic beam. And you can just balance the release of elastic energy, because that's zero curvature for something that's naturally curved. So you can easily estimate the release of elastic energy per unit advance of the front. And you can balance it with some kinetic energy. Okay, so if you do that, that gives you a scaling for the velocity. I thought it was included, but right, this one. Just by scaling, though, that's consistent in orders of magnitude with this. Now you can try to be a little bit more accurate and see, can we have, well, first, can we calculate actually the number? So where does that come from? And can we also calculate the shape of the solution? So it's funny because we thought it was an easy problem, but it turned out to be slightly more difficult than we thought. And you can start by doing numerical simulations, by the way. And maybe you start by, isn't there a feature of the solution that maybe you weren't expecting, or is it exactly like? Yeah, it's lifting up. So there's actually, that's a good point. So forget about the details of the simulations. You'll never be able to find a solution that propagates on a straight line. It's slightly lifting up, and the position of the center of mass goes like the cube root of time. For actually a simple reason, if you think about it. So these are the equations of motion for the problem. It's the elastic guy, you recognize the kinematics, the tangent, center line and tangent compatibility, the curvature, and then the dynamical, the balance of linear and angular momentum, the constitutive law. And so this is a PDE, and you have an external force, which is the reaction force from the substrate. So that's the way you formulate the PDE. But again, it's nonlinear, so it's not easy to solve directly. But we'll be able to solve it in the limit of long time. So when we have this large front that's formed, and eventually we'll be able to select the velocity. So you can look at short times first, but that looks really like the spaghetti, and I'm going to spend a lot of time on it. So short time would be really the initial times where the slope is everywhere small, and then you get this dynamic beam equation, and you can find self-similar solutions exactly like with the spaghetti. If you look at the full simulations, it works nice because this short time simulation tells you that, so that's the SC is the arc length of the points that lift off. So it tells you that the size that has lifted off goes like square root of time. And Ym would be the elevation of the center of mass that goes like with time, and the two scalings are consistent. And even more than that, you have an asymptotic solution that works nicely. But for long times, it's more tricky. And so, as I said, the first thing you would try is to find some front-like solution, right? Some progressive solution. So you can just use this trial form of the equation, insert into the equation I was showing before, and see what you get. So what you get looks like that. So that's the bending modulus. That's some complicated function of curvature. And you find 0 in the right-hand side. And the 0 here, it's the inertia term that comes with the mass per unit length, right? So it's bad news because there's not really a way to select a velocity for a front with just elasticity and no inertia, right? So that doesn't work. So that's not the form of the solution. Then you can notice, as Peter was doing, that in the simulation, the coil is looks like it's continuously moving up. And actually, you can realize that the reason for that is that at this point of contact, there's a point-like force that's upwards, and that's relatively simple to see from the local balance laws. And so the vertical momentum has to be an increasing function of time, and that's not compatible with this. Okay, and so you can look at this movie again in the moving frame, in the frame that moves with the point of contact, and you indeed see that it's slowly moving. This is incredibly complex form. I mean,
even though you have to lift more weight.
Right, so there will be a quantitative argument, but if you do a balance on the this part here, which has lifted off globally, even though it's an open system, its momentum has to be more and more upwards. And we do exactly this. We do a balance of the force here and of the momentum of this open system. Okay, so this is rising steadily. What's happening there? So you could do a scaling analysis. You can assume that the radius here is some power of the time. Again, we are doing a long time asymptotics. We're trying to understand the scaling dose before we do something more quantitative. Okay, and so we are assuming two things. We are assuming that the typical radius here will be 2 to the power t to the power beta, and we are assuming that the position of the liftoff point will be t to the power alpha. So first, you can balance elastic and kinetic energy. So the elastic energy would be just the length, because we work in units where the natural curvature is 1, and so the amount of elastic energy that's released per unit length is of order 1, right? So the total elastic energy released here would be just the length. Now the kinetic energy would be, well, the kinetic energy of this part, so that would be the length, because that sets the mass, times the velocity squared. And the velocity squared is just the derivative of this. If you balance the two, you find that the SC cancel out, and you need to have alpha equals 1. Okay? So that's tricky. It's not a front-like solution like this, like S minus CT, but still, there's a well-defined velocity. So SC will be linear in time, at long times. Okay, now you can try to find this, and then we do a balance of linear momentum. So the linear momentum in the upper part will be this, so the mass here times the typical velocity. So let's see, the mass is t, because now we know alpha equals 1. The vertical velocity will be the derivative of this, so that's t to the power beta minus 1. And that you need to balance, and that's by the force here, and it turns out the force here is the derivative of curvature. So that's the third derivative of position. So you can get it in terms of beta. And if you do that, you find beta equals 1/3. So you find that the contact point moves with constant velocity, and the size of this grows like the cube root of time. You can test this in the numerics, and this works as expected. And again, same story. You have a long time. You're looking for long time behavior. So now you can look at the problem in rescale variables. We have numerics here. So we plot x divided by this cube root of t, y divided by this cube root of t, and this yields something like that's a reasonably steady solution. So now we are following the curve and also zooming out with this cube root of t behavior. And so what we expect here, and I'm not going to give you the detail, is that this file, it describes a self-similar solution. So the real system is going to stick to this spiral in rescaled variables. Okay, and so there's actually a quantitative analysis which does that. So now we are assuming that the shape anywhere is going to be okay. So that's a translation that moves to the point of contact. And then we assume that we have a universal shape R that's stretched with the t power beta in terms of a dimensionless variable u, which is s minus vt divided by this. So we are really assuming that this is universal in stretch variable, and we are bringing that back into the original variable. It's very like a boundary layer analysis. You need to bring that back into the original equations, and when you do that, you can find the solution, you can find beta, and you can ultimately find even the equation for this shape and the velocity and everything. Okay, so it's another problem where the long-time asymptotics is incredibly easier, simpler than the original problem, because as you see here, the s and t variable gets combined into a single variable, and you have a universal behavior. So the problem is to find this function R, which is a function of a single variable, while we started from a two-variable PDE. And just to conclude, the last few slides, one last slide. Just a take-home message that we've seen many times. Perturbation methods are incredibly useful for solving nonlinear problems. If you can identify a parameter which it makes sense to send to 0 or infinity, there are many situations where they are relevant, and the method is very often similar. There's an easy part and fun part, which starts by analyzing the scales and balancing the terms in the equation. And then if you know that, it's usually just a matter of introducing scaled functions and rescaling your problem and getting rid of the small parameter. And the problem you end up is considerably simpler than the original one, usually. Okay, thanks a lot for your attention, and I'll see you next week. If you, I went a little bit over the time. Maybe I should aim at finishing earlier. So if you have questions, you can ask. But I'll be around if you have
questions. So for this problem, so for example, you got some